Okay, welcome to EGR 550 Mechatronics class. And in this class, we are going to talk about mechatronics system. Mechatronic systems are mechanical and electronic systems. So what they do is you have an electronic hardware that runs some software and controls a mechanical system. If you think about it, robots, autonomous cars, for example, automation, even CNC, all these are mechatronic systems. So what I'm going to do in today's class is I'm going to give you a brief overview of the whole content. I will also talk about the labs that we are going to do and the equipment that we need to purchase to do the labs. So there are some students who are attending this session completely online. So what you should do is, if you are going to do it online all throughout the semester, you should purchase the required supplies and be ready to perform the experiments wherever you are. And if there are any questions related to that, I would be happy to answer. The course is easy, but there is a lot of content. And most of the content is going to be sort of hands-on. That is the reason why we have this classroom, which is like a studio, wherein the expectation is that during the first half of the class, there will be lectures, and during the second half of the class, the students will work on the mechatronics projects. And of course, I'm going to be around to help you out. So as far as possible, my recommendation to the students would be to come to class and attend in person. But if for some reason it's not possible, then you need to make sure that you understand the content and are able to do the labs on your own wherever you are. Because then I won't be able to hold your hands and walk you through some of those labs or the questions that you may have. The syllabus for this course is already uploaded on Canvas. I would strongly encourage you to take a look at it. So let me quickly discuss what we have in the syllabus. So if you go to mechatronic systems, here is the syllabus, and I will share the screen. So this is the syllabus for the mechatronic systems class. And as you can see, we have a Zoom link available. So you can attend potentially class via Zoom. But the intent would be to, yeah. The class number is different. That's all right. That's okay. The content is which class number? EGR 550, right?
Yeah, I think on the right it says Peralta 306.
Oh, the classroom. Yeah, that's Peralta. Initially, it was in Peralta 306, but I changed it to Tech 162. So that's because there will be some hands-on exercises. And I thought it might be a good idea if you have access to the power supplies and also the voltmeters, multimeters, and other equipment that you potentially need. So this course is for graduate students, which means there is going to be a lot of content. And my expectation would be that you would read some of the material and come to class prepared. There are a lot of resources that are available to study mechatronic systems. And what I would do is I will try to consolidate and compile the information and pass it on to you in sort of a condensed fashion. Now the textbook, this is considered as a Bible of mechatronics. which is an integrated approach. As you can see, this is a very thick book. And to be honest with you, I don't expect you to read through all the book, but trust me, I would be covering about 70 to 80% of the content in class. But if you have any questions, if you have any concerns, then you should go back and refer to the book. I believe there is a newer edition available, but older edition is fine too. If you go to Amazon, you would get the same book used for $12 or $15. So this book is a fantastic book. It also talks about mechatronic system, robotic systems, application, controls, and everything. So this would be the primary go-to resource. But don't let the size of the book intimidate you. The content is very straightforward, and I would be happy to discuss and go through it as we move through the course. The other important part is the lab. So mechatronics is not a spectator sport. You need to program the device. You need to get the data. You need to play with the hardware. You need to program the microcontrollers. Only then you'll understand the concept that we study in theory, how they are applied. For an example, we are going to talk about proportional, derivative, integral, PID control. But unless you use the PID control for an actual application, you will not understand how it actually works. So you need to get your hands dirty. Now there are different ways and there are different kits. Initially, I thought about giving a drone project, but then I looked at the background of the students and then I realized that quite about 70% of the students do not have background in aerial robotics. So I kind of decided not to do it. But if somebody wants to do a drone project as an option, that is still possible. So send me an email and I would be happy to discuss how the drone project would work. For an example, if you have some deep interest in aerial robotics, drone building, and previous mechatronics experience, then that would be a good project. If you don't have any experience in programming microcontroller using Python, Matlab, Simulink, Arduino, or even model predictive control, linear control, nonlinear control, system identification, machine learning, all that stuff, then this is going to be our best bet. Now, at this point, what I want to show you is the beauty of this is all the labs that we have in this mechatronic system course can be done with this simple, very simple setup. So there is an Arduino in the back, Arduino Leonardo. There are two heaters, two temperature sensors in front. There are LEDs and you can actually program this board using Python, Java, Matlab, and Simulink. So I would, and this is available on Amazon. Actually, it's available on Amazon Prime. So I would strongly recommend that before you come to the next class on Tuesday, please bring your own copy of this board. Everyone understood this? This will come. So I'll show you for the students who are online. So this is what you should bring to class. The only thing I don't know how it would work if you are attending this class online, but I will try to record as much as I can. And I will also point you towards the online resources, which actually explains the step-by-step video lectures on performing some of the labs. So what are the main components of this lab setup? So you have a thermocouple, a thermistor, you have a heater, you have an Arduino Leonardo, which is the microcontroller. Leonardo pins are mapped and we can use that. So we have two actuators and we have two sensors. Actuators are the heaters and thermistors are the sensors. And basically you can turn on and off, or you can change the cycle of these heaters based on the control logic or control algorithm that you use. It also comes with these two cables. So there is one cable which is to be connected to the Arduino, and I will show it to you in next class. But if you order, I want you to make sure that you have, so this cable gets connected to Arduino, and that is used to program the Arduino or to collect the data from the Arduino. And then this cable or jack gets connected to the top port, not the bottom one, top, because this is powering the heater. So what you can do is, if you actually don't need a full-fledged power supply, even though the power supply is provided over here. So what you can do is you can connect this to your Arduino, and you can connect your heater port to some USB, and then you should be good to go. You would be able to perform all the experiments, and those experiments are going to be fun. So my plan is, in today's class, I'm going to show you the software that you need to install on your computers so that we can do the labs. And then from next class onwards, we will have some lab activity where I would do the demonstration, maybe a complete demonstration or a partial demonstration, and the students would actually work on that lab. There is no final exam. As a matter of fact, there are no quizzes. There are all projects. Every project, I would be assigning a project in class. Typically, there will be one project for over 2 class periods. And at the end of a class project, what you will do is you will upload a very small report with taking some pictures. Sometimes those projects would have some theory questions. So what you should do is you should answer those theory questions as well. Now, let me quickly go to the second part of the syllabus. So if you go through the syllabus, we are gonna look at the Matlab, we are gonna look at the Python. And to be honest with you, I don't know what is the best course of action here. I would prefer to start with Matlab, but I will give you some hints related to Python. And if you click on the link that I just showed you, you can actually get to this temperature control lab. And if you have Prime, then you should be able to get it very quickly as soon as Saturday. So any questions on the temperature control lab from any of the students? Ideally, I wouldn't recommend a physical copy. If you get a physical copy, the brand new, it may be 150 bucks. You can get used copy for 12 to 15 bucks on Amazon, but you can get an ebook fairly inexpensive. So ebooks are very inexpensive. So you can get for, I think, 20 bucks or 29 bucks. That's good enough, because believe me that once you graduate from the program, this will be like a handy reference, even in your professional careers. For example, if I have a design problem, I still go back and review some of the material from this textbook to make myself comfortable. Okay, so next thing which I want to talk about is, let's see. So again, we had to follow the ASU face covering policy, the current face covering policy. my office is in the tech center. And if you have any questions, you're welcome to stop by my office or basically come see me. Even though it says you have homeworks and labs, but homeworks and labs will be combined as a project. So you will have some component of homework and some component of lab in one project. So there will be some lab breakdown. So, and again, for every assignment, I would kind of give you what is expected, and then I trust that you'll be able to do the project on time. And again, this is a summer course, so this is going to be certainly fast paced. So please make sure that you have enough time to do the assignments and do the labs. So there is a question. So typically, if you think about it, again, ideally, I would like to give you one lab project sort of assignments per week. But assuming some assignments take more time or some labs take more time, which is certainly possible, we can adjust that number. But I don't expect that you just keep those backlogged and try to work on those at the very end. As soon as the lab or the project gets assigned, I would strongly recommend that you get to it and do it. And most of the times you would be working on those labs and homework assignments in class. So that gives in-person students an advantage, but online students should be able to participate. I would also upload the video lectures. I would also upload the DIY material where how would you do the lab, how would you make the connection, what program you would program it and all. But this would be like sort of, we will adjust the pace as we go. There is no midterm, there are no exams, just projects, and each project will have a homework and a lab. Okay, all right. With that, are there any other questions that we can talk about? Now, one important resource which I want to talk to you about is APM, so AP Monitor. So AP Monitor is the optimization suite, and this particular setup was developed by this professor at BYU. This is actually a very good setup. And then again, as you can see, there are a lot of courses that utilize this particular content. So I want you, if you have your laptops up, just please go to apmonitor.com and then say take a course. So there are these online courses. How many of you are comfortable with Matlab? Everyone comfortable with Matlab? Yes, no. How about Simulink? How about Python? A little bit. How about Java? No? Okay. All right. Okay. So again, we can use multiple programming languages to program the board. My go-to tool is Matlab and Simulink, but if time permits, I would be happy to discuss Python and other stuff. So again, if you go down, there are a lot of, this is the professor who developed this. Now, I want you to go to this control using Matlab. So go to control using Matlab and you should be able to see dynamics and control. And then there is this temperature control lab. So this is called as the TC lab. And in this TC lab, this is how the setup is going to look like. So you have a temperature sensor, you have an actuator. So temperature sensor 1, actuator 1, temperature sensor 2, actuator 2, you have an LED, and then what you have is you have these different files that you can download and implement different controller algorithms. Now what you need to do is, first and foremost, here are the lab instructions. So we are going to go through these labs step by step. But what I would like you to do is I want you to go through this setup and troubleshooting. So at the end of today's class, what you should do is you should visit setup and troubleshooting, and then actually you can download and install temperature control lab. You can get the lab kit from Amazon. You can download the TC files, and then there are lab instructions, and then you should go to setup and troubleshooting. Now, if you are familiar with Python, if you want to do everything in Python, you can use Python-based scripting. If you want to use Matlab, you can use Matlab-based scripting. So what would you prefer? Would you prefer Python? Would you prefer Matlab, Simulink? So you can use anything that you want. I use Matlab because it's very intuitive, and Simulink is like a drag and drop block diagram algebra can be worked out. But depending upon what, any option is fine. So if somebody says I want to use new Octave, that's totally fine. So what I want you to do is I want you to go to this setup, and then I want you to go through this Matlab video. And if you want, there is a Python video as well. So please, and Simulink. So please go through these. So this is something, and it actually shows you how to make connections, how to get data, how to install the packages, and then basically install Matlab Arduino support, and so on. So everyone understood this? This is something that we will do in next class once you actually have the hardware. But if you want to get your hands dirty, if you get this thing, the setup before next Tuesday, I would encourage you to experiment with this. Everyone understood this? And this is actually a very powerful setup. So once you start playing with it, you would realize that you can do study P control, PID control, PI control. You can also run optimization. You can do control theory. You can do machine learning. You can do system identification. So what I'm going to do is, in every class, there will be a lab activity. Okay. I will come to the class. I will discuss the theory concepts. Perhaps I would work out 1 or 2 examples. And after that, each student, and this is the perfect setup. So each of you will work independently on a particular lab that is assigned for today. So I will discuss the lab, how it is done. I will demonstrate some part of the lab, or I will demonstrate the lab and I will ask you to modify, and then you would be doing the experiment. Same thing for the online students. that you are welcome to study it synchronously, which means when I am around, you can also do the lab wherever you are located, or you can do it asynchronously, which means I will upload the video lectures typically by the same day, and you can do that the very next day. But please understand that will give you very less time to complete the lab. But my suggestion to you would be, give yourself 1 week to finish the assignments for that week. Don't get backlog, because if you get backlog, the whole thing will get piled up. And if there are any questions and concerns, you can certainly talk to me or send me an email, and we would be happy to help you out. Any questions from online students before we start the lesson for today? Any questions from online students? In-person students, any question? So everyone understood? When you come to next class, you should bring this TC lab and try to go through the setup instructions for the TC lab. And you will find those setup instructions on appmonitor.com. Okay, now let me start with the content for today's class. So now I'm going to ask you a few questions before I actually start discussing. How many of you have taken a basic control theory class as an undergrad? For example, system dynamics and controls or linear control theory. Anyone? Huh? Okay. So online students, did anyone take basic control theory class? Now I'm gonna say few things, or let me write few things and tell me how many of you kind of know these words. Okay, because these are the keywords that we are going to talk about in this class. So basic control theory or basic system theory. So intro to control theory. So first question to all of you would be, what is a dynamical system? You heard this word before, a dynamical system? Right. So dynamical system means a system that state of the system changes with time. A simple example for the dynamical system is, maybe you have a tank and you have a water flow and the height of water in the tank. So this water height or level changes depending upon the flow. So dynamical system is, yeah. Oh yeah, I thought I did. Let me see. Bear with me for a second. share content, screen. Log out. So it's not giving me the Zoom option. So bear with me 1 second. I have to log out of the Zoom and come back in. Oh yeah, Zoom needs to be updated. That's why. Okay, now it should work. Okay, so this is what it is. So dynamical system. So this is the dynamical system, and the water height is dependent on the amount of flow and the pressure differential across the tank. Now, next thing is you can think about a dynamical system can be represented by an equation. A simplest example is force is equal to mass times acceleration. This is the Newton's second law. So we have a mass m. On this mass, there is a force F, and this force F is going to cause an acceleration A. So force is a vector quantity, which means it has magnitude and direction. Acceleration is a vector quantity that has magnitude and direction. So what you have is, if you set up the positive direction in the positive x-axis, positive y direction in the positive y-axis, you can see that this force plus F is equal to m multiplied by plus A. So as force increases, the acceleration of the mass increases. Next question I want to ask you about, how many of you know something called as Laplace transform? Does anyone know what is a Laplace transform? Online students, any comments? Have you heard or seen what Laplace transform is?
Yes.
Okay, what is it in simple words?
If we have a system, we can change it to another system to solve it, because we cannot solve differential equation. We change the dynamic system to differential equation system to solve it.
Okay, so I'll tell you what that means in layman's language. Force is equal to mass times acceleration. So if I'm going to say x is the displacement, dx by dt is velocity, and d by dt of dx by dt is going to be the acceleration, which is also written as d2x by dt square, which is acceleration. So if I write down force is equal to mass times acceleration, force is equal to mass times acceleration, this is actually a differential equation. Now, why do we call it a differential equation? This is a differential equation because this includes derivatives. how many derivatives are there? So there are two derivatives because the order of the system is the highest order of derivative. So let me write this down. Order of the system is the highest order of derivative. If you want to solve a derivative equation or a differential equation, what operation do we perform? We perform integration. So if you have derivative, single derivative, you are going to integrate one time. If you have two derivatives, you are going to integrate two times. Do you agree with me? So this is the second order system. So logically, if I want to solve this second order system, I will have to integrate two times. Everyone agree with me? Now, what happens when you integrate? Every time you integrate, you land up with a constant of integration. Okay. So basically, if I want to solve this equation, what this means is I have to integrate two times and then add the constant of integration, somehow find the value of that constant of integration and plug it in there. That gives me the solution of differential equation. Everyone understood this? Now, again, for some of you, this may be revision, but what I'm going to do is I'm going to go from very basics. Because here is what I have seen. Students take advanced classes in controls, differential equations, dynamics, but fundamentals are not clear. And when it comes to the point that you have to use that knowledge to solve some practical problems, is a huge barrier because we cannot relate the theory content to the actual systems that we see in practice. So what is the stumbling block here? The stumbling block here is I have this equation, I have to integrate twice, right? And integration is not an easy thing. I mean, do you agree with me? Addition and subtraction is easier than integration. Do you agree with me? So what happens when we do the Laplace transform? In simple words, Laplace transform does the same thing to differential equation that logarithms do to multiplication. Let me tell you what I mean by that. Everyone has seen logarithms. Why were the logarithms invented? What was the need for logarithms? Why log? So, does anyone know? So think about it. If I have this big, long number, like I'm gonna give you a number 1, 2, 3, 4, 5, 6, 7, 8. This goes all the way up to 10, all the way to 20, something like that. This is a long number that needs to be multiplied with another long number, 1 all the way to maybe 9 somewhere. Do you agree with me? Performing this calculation manually is a very time consuming task. For example, even if you have a calculator or a computer, it will still take some amount of time. What happens when we take the logarithm of this number? What happens when I take the log of this number? Log of this number is a very large number, will be a very small number like this, right? This is what I do. So now I'm taking the log of this number. And how do I do the log of number? I don't calculate. I look at the tables. I look at the tables and find out what is the log of this huge, big number. Log tables are given to you. Then what I do is I find the log of this number. And I get this another small number. And this multiplication operation gets converted into an addition operation. And since these are two small numbers, this addition should happen, or you can do it in no time. And then what you do is you take inverse log of this, and now you have this huge number which happens to be the solution of this equation. That is the fundamental purpose of logarithms. Logarithms convert a multiplication operation into an algebraic operation. So log will take this multiplication operation and convert that into an algebraic operation. Laplace transform would also do the same, but it will take the differential equation and convert it into an algebraic, which means addition or subtraction equation. So now think about it like this. You have a differential equation. You take the Laplace transform. That super complicated differential equation gets represented as addition or subtraction, which is very easy to solve. Then whatever answer you get from that addition and subtraction, you take the inverse Laplace transform, and now boom, that's the solution to the differential equation. And that is why the Laplace transform is used. Everyone understood this? And I will get into the mathematics of Laplace transform as we get to it. But first, let me introduce some of these concepts that perhaps you studied in your undergraduate education. Okay, the next concept which I want to talk about is the concept of Fourier transform. Have you heard or seen the word Fourier transform? Can someone tell me what Fourier transform is? Okay, a step back. What is a Fourier series? So idea is you have a periodic signal. So you have a periodic signal. The periodic signal is like signal that is repeating. So this is a periodic signal. And it can have multiple frequencies. This periodic signal can be decomposed into its components, like you have different sines and cosines. And when you add these together, what you get is you get the Fourier series. So you have a periodic signal, and think about it like the light spectrum. So you have a prism, and basically a ray of light hits the prism, then you get diffraction, and then you get the light spectra. So you have this signal, and what we are doing is we are doing this decomposition into its constituent parts. Now Fourier transform comes from the Fourier series. So if you take a Fourier transform or the numerically better algorithm, something like fast Fourier transform, that will give you the frequencies in that signal. So Fourier transform is a very, very important tool that is used in signal processing, uh, image processing, audio video processing, and so on. Fourier transform are related to Laplace transform. And if you think about all these transforms, so what are these transforms? So transforms are, you take a function, multiply the time series that you have with that function, and perform something called as integration. Depending upon the function that you use, that is called as the kernel. Depending upon the kernel that you use, you get a Laplace transform, or you get a Fourier transform, or you may get a different transform. So the idea of transform is, you have the original signal, you multiply that by a function and perform integration if the signal is continuous, or do running sum or convolution if the signal is discrete. In mechatronic systems, we are always going to deal with digital hardware, so which means the integration, which is in continuous domain, will be represented or replaced by convolution in the discrete domain. So this is the Fourier transform. Next thing, the important word that I want you to think about is something called as the Bode plot. Does anyone remember what a Bode plot is? No? Okay. Now I'm going to ask you a very simple question. How many of you have used a washer? It's a very simple question. Everyone, right? Okay. So imagine you have this washer. Doesn't matter whether it is front loaded washer or the top loaded washer. So say I'm going to say this is a top loaded washer. Okay. And what I do is I fill this with dirty clothes and then basically run through the cycle, and then actually at the end of it there will be wash, that goes to rinse, that goes to spin cycle. Are you with me so far? Wash, rinse, and spin. Now what I'm going to do is, I have this motor here. This is the motor or the tub that rotates. I'm going to attach a tachometer to this. So I'm going to measure the speed of rotation, speed of this motor. And you agree with me, during spinning, the motor speed changes. Initially, it's spinning at slow speed, then it starts spinning at a higher speed, and then gradually it slows down and eventually it stops. Do you agree with me? And what I'm going to do is, here, I'm going to use some type of a displacement measurement device, maybe a micrometer or maybe some type of an accelerometer. So I just want to measure how much it vibrates. So basically, I'm going to call this a vibration meter. Vibration. So now I want you to imagine that this washer completed its wash cycle, rinse cycle, and it started spinning. Okay. What would happen? Initially, the tub is spinning at so slow speed, but the whole washer is not going to vibrate. It will vibrate slightly. So what I'm going to do is, I'm going to have the spin speed over here, and I'm going to have the amplitude of vibration. initially the spin speed is small, so the vibration amplitude is small. After some time, the spin speed increases. What usually happens? So the vibration amplitude increases. Have you seen that? So let's see something like this. Then what happens? It increases further. So spin speed increases further, the amplitude increases further. Spin speed increases further, and then the amplitude is maximum. You feel like the whole thing will come apart, but it doesn't, because there is something holding it together. If the washer was not held in place, then probably it would just disintegrate itself. Then as speed increases further, what happens? The amplitude drops down, amplitude drops down, amplitude drops down, and you would see something like this. And as the spin speed is decreasing, the washer tracks the same trajectory. Do you agree with me? Something like this. So what is this plot? This is the plot of amplitude versus omega, which is the angular speed. This is essentially the body plot. Now, if you think about the body plot, you have this system, and what I'm going to do is I'm going to feed this system with different frequencies, and at different frequencies, I'm going to measure the amplitudes. So I would have A1, I would have A2, and I would have A3. So at omega 1, I have A1, at omega 2, I have A2, at omega 3, I have A3. So I'm gonna get these amplitude frequency pairs, and I'm gonna plot those on one plot, and that plot is nothing but the body plot. Everyone understood this? Now, why do we need to do this jugglery? The reason for doing this jugglery is because for understanding the systems, our first and foremost approximation is the system is linear. What do I mean by linear? Linear means you go to McDonald's, you pay $1, you get one burger. You go to McDonald's, you pay $2 and you get 2 burgers. But there's a deal in McDonald's. If you pay $3, then you get 5 burgers. That is an example of a nonlinear system. So what we are doing is we are assuming the systems that we deal with in practice are linear. And what is the fundamental advantage of linear system? That is, they are easier to analyze, and they satisfy the simple condition like additivity, which means if you add multiple sources, their resultant will get added as an output of the linear system. Then basically you can actually use something like a convolution, and if you have different frequencies, you can study the response of that linear system to those different frequencies and understand the dynamical equation of the system. So system identification, understanding the state evolution, how the system is going to behave in future for linear systems is very simple. Companion plot to body plot is something called as the phase plot. What is this phase diagram? So phase diagram is you have the speed on the x-axis, and you would see how far the output is delayed compared to input. So for an example, if your output has, so let me give you an example what that means. So if you have a signal and you're feeding that signal to a system. So think about it like this is the input, and you would notice that the output is kind of delayed. So output starts from here. So this is called as the phase lag phi. So this is input. And this is output. And phi is the phase lag. And this phase lag is function of omega, or the frequency of the input signal. So the idea would be how far or how ahead of the output signal or the input signal the output signal is. So output of the system, does it lag by 90 degrees? Does it lag by 180 degrees? Does it lag by 270 degrees? Does it lag by 360 degrees? If it's lagging by 360 degrees, which means the output and input will be superimposed. So basically the phase plot is going to give you an indication of how far the output is from the input. So the time you start input and time you get output, how much is the phase? Now, one thing I just want to tell you, you can view this on this a 360-degree circle. So for an example, if your input is going to start here, input signal starts here, but you start getting output from here, which means you have 180 degrees out of phase. If your input is at same point, but your output is now here, then you would say it is 90 degrees out of phase. And this phase and phase plot and the amplitude plot, they are integral components of Bode plot. Everyone understood this? The next important concept is the concept, and this is a very important concept, is the concept of stability. And from this concept of stability, I'm going to talk about something called as the root locus, but this is the crux of linear system theory. Stability. So no matter what you study, whether you study in frequency domain, amplitude domain, whether you study with polar plots, Bode plots, or any other Nichols plot, stability is very important. So for linear systems, now there are three types of stabilities. So think about, like we have a bowl and there is this marble, and basically you tap the marble and displace it from its equilibrium position. So initially the marble is somewhere over here. You tap the marble, so the marble will get displaced and it will go back and forth, and finally settle down to its equilibrium position. Do you agree with me? So if I were to plot this, this is going to look like this. This is called as asymptotic stability. Which means the system is in equilibrium. You displace the system oscillates above the equilibrium, but finally it goes to its original position. Everyone understood this? The next case is same thing, but now this is rolling on a flat surface. Now what happens if this marble is rolling on the flat surface? Clearly, if you displace this marble will go to some other point, or this will go to some other point and get an equilibrium there. So which means it will again will not run away, it will go to the equilibrium, but that equilibrium point or that rest point will be different than the initial rest point. So this is called as simply stable. And the last case is something like this. When you have a marble which is on the bowl which is upside down. So if you push this, if you displace this, the system, this marble will get displaced and this will become unstable. Everyone understood this? Any questions here?
Stable is like the same angle.
It's a flat surface. This is flat. So it means it will go to rest, but the rest position would be different than its initial equilibrium position. Unstable means you displace it, it's never gonna come back. Everyone clear about this? Now, yeah.
So it's unstable because it's never going to come back to the original equilibrium position, or
and it will continue. So basically, it will never. The response, essentially, what would happen? What it means is the response will become unbounded. What that means? The response will become unbounded. Now, mathematically, what does it mean? And the best way to understand this mathematically is understanding a very simple concept of a differential equation. So I would say dx by dt is equal to a times x, or x dot is equal to ax. X is a function of time. Dx by dt is also a function of time. X is the dependent variable. T is an independent variable. Do you agree with me that this is a differential equation? And I would like to solve this differential equation. What do I mean by solving a differential equation? So let me put this question. What do I mean by solving a differential equation? Tell me, what do I mean by solving a differential equation?
finding particular values for the constant A, so that you know how x dot is different from x.
Okay. Now what I'm going to do is I'm gonna kind of give you a very a simple example. This differential equation that we have has a left hand side and it has a right hand side. So I'm trying to find out the value of x in such a way that when I substitute that value of x on the left hand side of the equation, and if I substitute that value of x on the right hand side of the equation, the left hand side is equal to right hand side. And that's what it means by equation or the solution of the equation. A simple example is 5 apples are for $10. So what I'm trying to do is I'm trying to find out the value of the apple. So if I substitute 1, agree with me, 5 times 1 is not equal to 10. As soon as I substitute 2, I know that 5.5 multiplied by 2 is equal to 10. The equation is satisfied, and that tells me that 1 apple is $2. Do you agree with me? So I'm going to do the same thing. I'm going to substitute the value of x on the right hand side, a function x on the right hand side. I'm going to take the derivative of the same function and substitute on the left hand side. And if the left hand side is equal to the right hand side, then that is the solution of the differential equation. Everyone understood this? That is what it means. In other terms, I'm trying to find out the relationship between the independent variable and a dependent variable. Some function, there's some function. I'm trying to find out this function. If I substitute this function on the left hand side of the differential equation and the right hand side of the differential equation, I get the same answer. Everyone understood this? Now, I want you to look at the differential equation that you have in front of you. X dot is equal to ax. And tell me, what is the simplest function I can substitute that would equate the left hand side to the right hand side? What should I say x is? So I want the left hand side x dot ax. Can I substitute x is equal to 5? So if x is equal to 5, x dot is equal to 0. Do you agree with me? So I have 0 is equal to 5x. 0 is equal to 5a, right? Left hand side is not equal to right hand side. So clearly this is not the solution. Now check this out. If I substitute x is equal to 0, x dot is equal to 0, can you see that I get a left hand side 0, a times 0, 0 is equal to 0, so which means 0 is a solution of that differential equation. Does it make sense? But that is called as the trivial solution or not important solution. 0, x is equal to 0 is a solution, but it is called as the trivial solution. Are you with me so far? So if I want to find out the non-trivial or the actual solution, what should I do? Clearly, this is a differential equation. What is the order of the differential equation? So can someone tell me what is the order of this differential equation? Order of a differential equation is the highest order of derivative or number of dots. How many dots do we have? 1. So the order is 1. So I need to integrate this once. To find the solutions. Are you with me so far? So what I'm going to do is I'm going to integrate this equation. So dx by dt is equal to ax. Dx divided by x is equal to a times dt. I will have to integrate on the left hand side and on the right hand side. What is the integration of 1 over x? Ln of x. What is the integration of A is a constant, integration of dt is t plus a constant of integration c. Let c is the constant of integration. Now I'm going to take the exponent on both sides. So there will be e here and e here. So this becomes x of t e raised to at multiplied by e to the power c. This is a constant. So I get the solution x of t. I'm going to call this a e to the a. Yeah, agree with me? So if you have a differential equation, which is shown over here, if you have a differential equation which is shown over here, after you perform the integration, if you add appropriate constant of integration, the solution is a e to the at. Are you with me so far? And this equation is the crux of the stability theory. And we'll stop here for 15 minutes and then we'll come back. We'll talk about the stability pertaining to this particular equation. So you will have a break of 15 minutes. I'm gonna pause. So if you look at what we have done so far, is we solve this differential equation and we got this solution x dot is equal to ax. The solution is x of t capital A e to the at. Now what I want you to do is I want you to think about three cases. So the first case which I want to talk about is if A is equal to 0. If A is equal to 0, what would happen? Do you agree with me? X of t is going to be A. What that means is no matter what the time is, the value of x will be constant. You agree with me? Now let's look at the case A is less than 0. What happens if A is less than 0? X of t will be A e to the minus at. So this as time goes on, this has to decrease. So this would be like this. Do you agree with me? What happens if A is greater than 0? X of t is equal to A e raised to at, and the solution will be positive. You agree with me? Now I want you to think about the material we talked about earlier. This is simply stable. This is asymptotically stable. And this is unstable. this. So what it means is whether A is negative, A is 0, or A is positive decides the stability of the differential equation. So the important point here is stability of this differential equation depends upon sign of A. Means whether A is positive, A is 0, or A is negative. Everyone understood this? Now please understand this A is a scalar quantity. A is just a number, a single number. Are also called as the scalar. For an example, 1, 2, 3, 5, etc. What happens if A is a matrix? Now, what does that mean? Now, for that, what we want to do is we want to understand the concept of something called as the state space. But still, let me actually give you an example. Say you have a system, something like x dot is equal to minus 5x, y dot is equal to minus 3y, and I want to write this equation in a matrix vector notation like x dot, y dot is equal to minus 5, 0, 0, minus 3, x and y. Do you agree with me? So if you do first row, first column, the equation that you have on the left hand side can be written as a matrix or a vector matrix equation. So this equation, I'm going to call this guy as x. I'm going to call this capital A, and I'm going to call this x. So what I have is I have this matrix differential equation it's x dot is equal to A x. You can do the same thing if you want to find out x of t. You can do the mathematical jugglery that we did earlier, and instead of taking the exponent of a number, you can do exponent of a matrix. And that gives you the solution of this system. So this is called as matrix exponent. And the stability of this equation, stability of the matrix differential equation it depends upon eigenvalues of the matrix. Now, what does this mean? If the eigenvalues have negative real parts, the system is asymptotically stable if eigenvalues have zero real parts, the system is simply stable and if eigenvalues have positive real parts, the system is unstable. So now what I'm going to do is I'm going to just rewrite this. So so that we understand what is going on. So the eigenvalues in general of matrix in general are complex, which means you can have A plus IB, where I is square root of -1. A is the real part and B is the imaginary part. If the eigenvalues A are in the left half plane, the eigenvalues are here, system, so this is the real part, this is the imaginary part. System is asymptotically stable. If the eigenvalues are in this part, system is unstable. And if the eigenvalues are on here, imaginary axis, the system is simply stable. Are you with me so far? Now let's take a very simple example. So let's look at that we have this mass, okay, on this mass, there is this spring. On this mass, there is this spring. And what I do is, I pull this mass towards right. And then let it go. I pull that mass and let it go. So if I were to look at the free body diagram, this means I construct the forces that are acting on this mass. I got the spring force K times X acting in the left-hand side direction. I got the inertia force acting in the right-hand side direction. So applying summation of forces is equal to mass times acceleration minus kx is equal to mx double dot. So I have this equation mx double dot plus kx is equal to 0. This is called as the differential equation of motion, which is differential equation of motion for spring masses. So in the free body diagram, what you do is you look at the forces that are acting on the mass, and then you'll notice that as you pull the mass towards right, there is a spring force towards left hand side, and since the mass is going towards right, acceleration is towards right, so you got inertia force mx double dot towards right, and you have this equation mx double dot plus kx is equal to 0. Now this equation is a second order differential equation. Why it is second order? Because please understand there are two number of dots. There are two dots. So this equation is second order. Which means if I want to solve this differential equation, I have to integrate this differential equation 2 times and add 2 initial conditions. Now there is another way of looking at this system. This is the second order differential equation. This can be converted into a set of 2 first order differential equations, which is called as the state space. So what is the state space? Is the space spanned by system state variable. So how do you know what are the state variables? You can choose state variables the way you want, but it is customary to start with the zeroth order derivative system. So for an example, if you have this equation mx double dot plus kx is equal to 0. What is the zeroth order derivative? Which is x. So which is the first state? State is x. What is the derivative? Which is x dot. So these two are state space variables. So x and x dot are the state space variables. X is the displacement, x dot is the velocity. As you know, d by dt of displacement is velocity, and d by dt of velocity is acceleration, that is nothing but minus k by m x from equation 1. So if you look at the first equation, that is simply saying that you have the displacement term here. I take the derivative of the displacement, I get velocity. Second equation is saying I take the derivative of velocity, I get acceleration, which is minus k over m x. Now these two equations, so equation 3 and equation 4, can be written as in matrix vector form. I would say d by dt x dot is equal to, I'm going to have the same state vector here, x dot. Can someone tell me what should I fill in the blanks? So here, this is a 2 by 2 matrix. What would come in the first row, first column of that matrix? So I have equation 3 and equation 4. I need to represent this equation 3 and equation 4 as a matrix vector equation. This will be 0. This will be 1. What would be here? Minus k by m and 0. You agree with me? This is called as the state space representation of equation. You agree with me? Any questions here? Okay. Now what I want to do is, I want to add something to it, which is called as, I'm going to add damping to it. So now we have spring, we have a damper, and we have a mass. This mass, spring and damper. If I write down the differential equation of motion, I have to draw the free body diagram. Kx Kx dot Mx double dot. So your equation is going to be minus Kx minus Cx dot equal to Mx double dot. This becomes Mx double dot plus Cx dot plus Kx is equal to 0. Now, if I were to follow the same process that I have done here, I would retain the same state space variables, x and x dot are my state space variables. And this equation, now I'm going to ask you to help me out here. is equal to this matrix here, x, x dot. Now please help me out here. What would be first row, first column, first row, second column, second row, first column, second row, second column? Tell me. What is the first relationship? First relationship is, what is the relationship between x and x dot? If you take d by dt of x, you get x dot, right? This is my first equation. So d by dt of x is x dot. Everyone understood? First row, first column. Now the second is, I need to write this equation, which is x double dot is equal to minus c by m x dot minus k by m x. Do you agree with me? So this equation gets written as minus c by m and minus k. So this is the state space representation. Now, if I ask you, this system, tell me, comment about the stability of this system. So this equation is x dot is equal to a x. Now my question is, comment about stability. So whether the system is stable or unstable, what would you say? How do you find out whether the system is stable or unstable?
You can graph it.
You can graph it. The easiest way is find the eigenvalues of A. So this is A, right? Find the eigenvalues of A. If the eigenvalues of A are in the left half plane, and what do I mean by left half plane? This is called as the left half plane, LHP. If the eigenvalues are in the left half plane, the system is asymptotically stable. If the eigenvalues are on the imaginary axis, then the system is simply stable. If the eigenvalues are on the right half plane, which is RHP, the eigenvalues are on the right half plane, the system is unstable. So if you have a matrix differential equation, then what you do is you find out the eigenvalues of the matrix, and that would tell you about the system stability. Everyone understood this? And in next few lessons, we will actually use Matlab and study the system stability. But in this particular class, I want you to simply understand that you have something called as the time series representation, and then you can actually get that into I can find the eigenvalues, and that gives you the stability. Now at this point, I want to touch upon an important concept. Is I'm not going to talk about the mathematics of it as of yet, but I want you to understand the how to use that theory. So there is something called as time domain. And there is something called as S domain or Laplace domain. So in time domain, independent variable is t. In the Laplace domain, independent variable is s. In time domain, the dependent variable is x of t. In Laplace domain, the dependent variable is x of s. If you have the derivative in time domain, d by dt, in Laplace domain, that is given as s. If you have integration in the time domain, the Laplace domain, it is given as 1 over s. Now what I want to do is, I'm going to write down a differential equation in time domain, and we will try to convert that differential equation into Laplace domain. So first differential equation which I want to talk about is mx double dot plus kx is equal to 0. So m is a constant, so m would remain as is. X dot is the derivative. There are two derivatives, so this will become s square x of s plus k x of s is equal to 0. So you can see a differential equation in the time domain and the representation of the same differential equation, the Laplace domain. Now, what is the major difference between the time domain equation and the Laplace domain equation? Please understand, if you look at the Laplace domain equation, the derivative is gone. You agree with me? Which means there is no dots. There is just, and this is a differential equation. And this is an algebraic equation. So what did Laplace transform do? Laplace transform took the equation in time domain, a differential equation in time domain, and converted that into an algebraic equation in the Laplace domain. Everyone understood this? Now, one important thing, if you have an input, which is u of t, in Laplace domain, the input is going to be u of s. So this is u of t, which is the input on the time domain. That is u of s is the output and input in the Laplace domain. So this brings me to an important question. That question is, what is a transfer function? Transfer function is the Laplace transform of output divided by Laplace transform of input. Now, let me explain this with an example. So if we have a mass, there is a spring, and on this spring mass system, there is an external input u of t. Displacement of this mass is given as x of t. So let's identify. This stiffness is K, this mass is M, this is input, this is output, M is mass, K is stiffness. And the differential equation in the time domain is mx double dot plus kx is equal to u of t. I'm going to take the Laplace transform of everything. M is going to remain as is. X dot is s times x of s. X double dot is s square x of s. So I will write this down as s square x of s plus k x of s is equal to u of s. Then I would take x of s common outside, ms square plus k x of s is equal to u of s. Now u of s is the input, x of s is the output. So transfer function is going to be x of s divided by u of s equal to 1 divided by ms square plus k. So this is called as the transfer function. Everyone understood this? So system dynamics or a dynamical system or system that is varying with time can be expressed in time domain. It can be expressed in the Laplace domain, or you can represent the whole thing as a transfer function. So think about transfer function as a black box. Think about transfer function as a black box. You provide some input to this transfer function and you get some output from the transfer function. So you have transfer function that takes the input and basically you multiply the input by the transfer function and that gives you an output. Everyone understood this? And very simply, transfer function is the Laplace transform of output divided by the Laplace transform of input. Everyone understood? Laplace transform of output divided by the Laplace transform of input. Any questions on the material discussed so far? So next point which I want to discuss is the concept of open loop and closed loop system. So let's understand what do we mean by open loop system. So in open loop system, you have a system. Say for an example, you have a system transfer function. You have some input and you have output. This system is, say this is system. This is called as the open loop system. Now, what is a closed loop system? In the closed loop system, what you have is you have the feedback from the output that somehow is fed into the input. So you have something like this. So this system is feedback this is how, and this is called as the summing junction. You have input and you have output. Now you can have, if this is negative, you can have a negative feedback system. If this is positive, then you have a positive feedback system. So this is called as open loop system, and this is called as the closed. Now a very simple example. For example, I'm teaching, okay? If I just keep on teaching without asking you any questions or seeking your feedback, that would just be open loop teaching. But if I stop, if I ask for feedback, and if I alter my teaching methodology or speed accordingly, that's a closed loop system. For an example, if you look at the 3D printers that we have in the Innovation Hub, they run on a stepper motor. Stepper motor is an open loop system. You give the command, the motor goes. You don't know where the final position is, and you don't compare that with your initial command. If you have a servo motor, wherein you have a motor, and at the back of the motor, you have some type of an encoder or resolver. So what you do is you track where that motor response is, and that's a closed loop system. So open loop systems are used when the systems are not, the dynamics is very well known. So you know, if you supply certain type of input, you're gonna get certain type of output. Closed loop systems are used to basically track the error, just to make sure that the output is tracking the desired system. So negative feedback system are the most common system used. So let me look at the transfer function. So if you look at the open loop system, it is shown like this. You have G of S. This is open loop system. Closed loop system, you have G of S. This is the summing junction. You have H of S. And you're going to have this as U of S, and this will be X of S. This is U of S, this is X of S. So if you look at the open loop transfer function, it is going to be X of S divided by U of S is equal to G of S. This is called as the open loop transfer function. Now I want you to understand the closed loop transfer function. So if you think about the closed loop transfer function, you have U of S is coming here, X of S is going out, X of S is coming here. So here you have H of S, X of S. At this junction, what you have is you have U of S minus H of S, X of S. Here you have x of s is equal to u of s minus h of s x of s g of s. So if you expand this equation, you have x of s is equal to u of s g of s minus h of s g of s x of s. So in the last stage, I'm going to take everything on the left hand side. So x of s plus h of s g of s x of s is equal to u of s g of s, which means finally, if when I do x of s divided by u of s, this is going to be g of s divided by 1 plus g of s. This is called as the closed loop transfer function. This is called as the open loop transfer function. This is called as the closed loop function. Everyone understood this math, or do you want me to work out this math again? So please understand, for the open loop transfer function is x of s by u of s is g of s, and for closed loop transfer function, g of s divided by 1 plus g of s h of s is the closed loop transfer function. Everyone understood this? Any question? So few things about this transfer function. This transfer function has a numerator and it has a denominator. And s is an independent variable. So there is a possibility for some value of s, your numerator could become 0. So please understand, since s is an independent variable, for some value of s, denominator of s could be equal to 0. If denominator of s becomes 0, then transfer function could become infinity. These are called as the poles of the transfer function. So poles are the values of s when the transfer function becomes infinity. Poles are the values of s when transfer function becomes infinity. And for some values of s, for some ss, the numerator becomes 0. That means the transfer function reaches 0. They are called as the zeros of transfer function. So the zeros of the transfer function means the values of s when the numerator becomes 0, and the poles of the transfer function means when the denominator becomes 0. Zeros and poles, they are very important when we talk about the transfer function and transfer function analysis. Okay, so what we have done in today's lesson? In today's lesson, we talked about, yeah. Okay, so let me quickly review. Believe it or not, we covered a significant amount of material today, and it may seem overwhelming, but believe you me that we are going to dig down deeper into all these techniques and actually perform some experiments that would make complete sense when we look at the mechatronic systems. So first and foremost, we looked at the concepts in control systems. We tried to understand what is a dynamical system. Then we looked at what is the Laplace transform and how is it important to understand and analyze the dynamical system. Then we looked at a simple concept of Fourier series, which is used for signal decomposition. We talked about the Bode plot that allows us to find the frequency response or the amplitude of and phase of the system subjected to varying frequency input. We looked at the concept of stability for linear system. What do we mean by asymptotic stability? What do we mean by simple stability? And what do we mean by system is unstable? Next part, we looked at the concept of Eigen Values. What dictates the stability of the system? If the Eigen Values are in the left half plane, the system is unstable. The Eigen Values are on the imaginary axis, system is simply stable. The Eigen Values are on the right half plane, the system is unstable. And this is what we showed with an example. That we looked at how to convert a simple system and convert it into a state space form. And then how do we analyze the state space equation? We looked at a simple spring mass system, and then we looked at the Laplace transform representation of it, the state space representation of it, and then we looked at how do we solve these problems. These problems can be solved using Matlab or some numerical technique, or in very limited cases, you can use analytical techniques to solve these. The relationship between the time domain and frequency domain. Then the concept of transfer function. What is the transfer function? It's the Laplace transform of output divided by the Laplace transform of input. And we took a simple example and found out the transfer function. We looked at the open loop system, we looked at the closed loop system, and we found out the transfer function of an open loop system, and we found out the transfer function of the closed loop system. And at the end, we discussed the concept of zeros and pole. Zeros are the values of s, where the numerator of the transfer function is 0. Poles are the values of s when the denominator of transfer function is 0. Everyone understood this? Now this is the part wherein we are going to do a lab activity. And since you don't have the TC lab set up with you, so I want you to go home and first foremost, if you have not done already, order TC lab from Amazon. Second, complete setup of TC Lab from apmonitor.com and apmonitor.com website I showed you. Third, install Matlab. And then Matlab Arduino. And Anaconda Python. And fourth, run demo scripts. Everyone understood this? So there are demo scripts for Matlab. There are demo scripts for Simulink. And there are demo scripts for Python. So what I want you to do is, I want you to run the demo scripts and what to upload. So for project one, upload in Canvas. Snapshots of your setup and video. Everyone understood this?
Is it the demo in your website?
So if you go to apmonitor.com, remember the website that I showed you, you have to go to Dynamics and Control, Temperature Control Lab. There are Matlab scripts, then there is a Python script, and there is Simulink script. You have to download those all, run those on your computer, and then take a snapshot, either using a phone or something. Just take a snapshot of system working and take a small video and upload that in project one.
Okay. But do you need like for all Matlab, Simulink?
Yeah, just one. So basically snapshot of Matlab, Simulink, one snapshot for Matlab, one snapshot for Simulink, one snapshot for Python, and one video. So one snapshot each. And video of system working. And I'm not very picky about how you want to do the video. You can just take a one video. So what you can do is you can open Matlab, Simulink, Python, run one by one and take a video. Everyone understood this? I just want to make sure. Does everyone know where to go? I'm going to show it once again, one last time. So this project is due next Wednesday. So due next Wednesday. And the reason I'm saying Wednesday, because if you have any issues, I can answer those in class. Okay. Online students, any questions? Let me show you one more time quickly where you will see what exactly I want you to do. So please follow my lead. So going back all the way from basics. Yeah, I know. So first, go to, go to apmonitor.com. apmonitor.com. Everyone with me? Then take a course. Then you go down and then you can go to process dynamics and control. And then go to temperature control lab. Everyone with me so far? And here you would see the setup. Here what you should do is go to setup and troubleshooting. So this is the link, AP monitor, copy, and I'm going to put it in the chat window real quick. So you have it. Can you see this in chat window? Everyone got it in chat window? On in-person students, everyone know how to get there? And then I want you to first look at this Python. It's a 10-minute video. Then temperature control Matlab and Simulink lab. If you click on this, it will show you step by step how to go to GitHub, how to download, how to make the connections, how to acquire data, and how to troubleshoot. So just read through this and watch through this. And then at the end, these are the scripts, and you should be able to run these labs. So please run these labs, or if you're not able to do it, again, there is this installation, installing, everything is here. So this is everywhere. There are videos. If you are using Linux, if you are using MacBook or iOS, you can actually run through this. And then try to do this. If you are not able to get it done, we will actually do the setup on Tuesday. But some familiarity with this would be really good. Because once that is done, we have covered enough basic. So we can actually start, we can jump into something like linearization, first order, and first order with a delay, Laplace transform, transfer function, state space. So we should be able to finish off these labs really quickly. Once again, I know some of you are attending this lesson or these lectures online, but it will be beneficial if you come to class and do the experiments with me, so that if you get stuck, I would be able to help you. Everyone understood this? So I'm going to stop here and then answer any questions you may have. Any questions, anyone? If there are no, yeah.
For future labs, we will use the same website.
Same website. So same setup. So again, I completely understand today's class was like a lot of theory coming at you at once. and probably you felt like brain fog after some time or brain fry after some time. Unfortunately, mechatronics is not a spectator sport. I can keep on writing the equations, but they won't mean a thing unless you play with the hardware. So whatever theory that we have discussed, once you play with the hardware, once you use Matlab, once you program, once you add P control, D control, look where the poles are, how the pole, what is the lead compensator, what is the lag compensator, then that will give you a better confidence. But believe you me, we have covered significant amount of theory material in today's class. So I'm going to stop here today. And in next class, we would have 50% theory and 50% hands-on labs. So please bring this setup to class next time when you come. Any questions from online students? Yeah, what is your question? Please unmute yourself and ask the question, or raise your hand or type your question. If there are no questions, I will see you in next class. So everyone understood? This is the link. If you want to just take a picture of it, or so AP monitor, PDC, index, main, Arduino setup. So I'm going to stop here, and I will see you on Tuesday.